So life was so much simpler back when I was young. When I first started doing sea ice work, I didn't have to worry about scales because I had a sea ice cover that was very well defined. It was an ice cover that was very well confined because it was in a tank. It was an ice cover that was 1 meter across and 20 centimeters thick. So I didn't need to worry about a wide range of spatial scales. And I didn't need to worry about temporal scales because if I wanted to have a melt season, I just warmed things up. Or if I wanted to freeze some more ice, I cooled things off. It was really a simpler time. But it wasn't long before I realized that there was more ice outside of the laboratory. And even though there were many things I could learn there were things beyond that. There were a range of scales, a range of many scales for sea ice processes and properties. Small scales, big scales, quick scales, and slow scales. And what I'd like to do this morning is take a look at some of those scales and put a qualitative framework into it. And so let's start off just by doing a power of 10 look at sea ice. We'll start off on a large scale, 100,000 meters across. And when we look at this scene, what we see are individual objects, ice floes with leads in between. And we see that they're come in different sizes and different shapes, but we see these individual features. If we zoom in an order of magnitude to 10,000 meters, we see things that are pretty much the same. We see an ensemble of flows separated by leads. This picture looks a little bit different because it was in the summer and we have melt ponds on, which is a recurring theme, at least for Arctic sea ice. And if we look at this, it isn't really that much different than the picture before. And indeed, if you're looking at sea ice on these scales, it's hard to tell how high up you are. There's a certain self-similarity that you see. And that can be of interest for a number of sea ice problems. But let's go in a little bit closer, another order of magnitude, looking at things on the kilometer scale. And now things have changed. Instead of looking at an ensemble of flows, we're looking at an individual flow. And if we look real closely, we can start to see that within that individual flow, there are features that might be of interest. See these faint lines here and there. And if we zoom in another order of magnitude to a 100-meter scale, we see those features a lot more clearly. Now, this is a picture taken in April when things are still cold. And we can say, oh, those are pressure ridges. And we start to see that they're all not the same. There can be some differences between them. And if we zoom in another order of magnitude, we see one of these ridges up close. It's a ridge that formed on ice that was fairly thin. It's a new ridge, and we just have this big pile of blocks. And if we took other 10-meter images, we'd see that these ridges come in a lot of different flavors, a lot of different sizes and shapes. So let's go in another order of magnitude and look at the meter scale. And now we're no longer in the spring, we're in the summer. We're looking at a melt pond. And I have to tell you, this is one of my favorite melt ponds. And the reason it's one of my favorite melt ponds is because it tells an interesting story. And that's, if you look at it, you can see that it has a bright side and a dark side. But if you walk across that pond and measure the depth of the water, it's the same everywhere across the pond. So we're not seeing an impact of the depth of water. And if we look at the ice is pretty much the same thickness across this pond. But part of the ice is very bubbly and the other part isn't. And so that tells us that the bubbles in the ice have an impact on what we see. And so that's an important thing to remember as we're talking about different scales, that there are linkages on what happens in one scale doesn't necessarily stay in that scale. It can propagate to other scales. So let's zoom in a little bit closer. Now we're on the 10-centimeter scale, and if you want to look at ice on the 10-centimeter scale, I guess you could put your face down on the ice, but usually what you do is you take an ice core and look at sections of that ice core. And that's what we see here. It's a horizontal thin section taken from an ice core and looked at under cross polarites. And what we can see, the different colors show us different ice crystals. And we see that the ice crystals have a scale typically of a few centimeters. Now, if you look really closely, you can see there seems to be some fine striations in these ice crystals. So let's zoom in another order of magnitude, and we see those ice crystals are made up of an ensemble of platelets. And these individual ice platelets are all nicely aligned within a crystal. And there's also some other stuff in there between the platelets, some darker looking things like that. So to see what they are, we have to go in another order of magnitude, down to a spatial scale of a millimeter, and we see that that object down here is an air bubble around a millimeter in diameter. And that's a typical size for air bubbles. They come in a range of different sizes, but that's a typical air bubble. Now, off to the side of it, we see another dark area. And if we zoom in another order of magnitude, we see that that dark area is a brine pocket. And I still remember my advisor telling me over and over again, it's the brine. It's the brine that makes all the difference. It's the brine that makes sea ice so interesting. Now, if we zoom into this, another order of magnitude, and it's cold enough, we can see that we can get solid salts precipitating inside the brine pockets. So that's a quick look over 10 orders of magnitude at sea ice. And you get the sense that there is some repetition to it. As we look at ensembles of floes, we also have ensembles of platelets making up an ice crystal, which makes up a piece of sea ice. So we have this wide range of spatial scales, and we have connectivity between the scales. Now, there's not just spatial scales. There are temporal scales. And nowadays, as has been mentioned, the sea ice is going away, at least in the Arctic, and that gets a lot of interest. So there's a lot of interest in Arctic sea ice from the perspective of climate change. And so that means we want to look at sea ice on decadal timescales. And what's shown here is a plot that, if you haven't seen this plot exactly, you've seen a similar plot. It's a time series of the minimum ice extent in September. The blue bars represent model ensemble runs. The black line is the average of those. We're looking at a couple hundred years here, and the red shows the observations. So we see that on the decadal scale, we're really interested in, first of all, observing what's going on, and then working to understand what's going on so we can predict future states. So there's a huge amount of interest now on decadal timescales. But really, what's a decade? It's just a bunch of years. So there's also interest in the annual scale. What happens over the course of an annual cycle? What happens over the seasons from winter, spring, summer, and fall? If you look at this in winter, it's cold and dark. We get a lot of ice production. In spring, even though it's still cold, the sun comes back. We start to lose ice around the periphery of the ice cover. And then we go into summer, a period of great ice loss through melting. And then finally, fall freeze up when the amount of ice goes back up again. So there's a lot of interest on temporal scales in terms of the annual cycle. And parts of the annual cycle are also very interesting. And one of them is summer melt. A lot happens in the summer. We go from this April scene of a nice snow-covered ice cover to August, when all the snow is melted, much of the ice is melted, there's a lot more open water, there's melt ponds everywhere. There are tremendous changes that go on during the summer, so we're very interested in that seasonal change from a temporal scale basis.
Where is that done? Where is that?
That's in the Beaufort Sea. It was taken during the Shiva experiment in summer of 1998. And we're also interested on the daily scale. Doesn't matter what happens one day or another day. Doesn't matter if it rains one day or if it snows that day. So that's a range of the temporal scales that we have. So if we put this all together, we've got a wide range of temporal scales. We have a wide range of spatial scales. How do we deal with all that? And so I think to get an idea of that, I thought I'd pick on an example and go through an example of one property that we look at on this range of spatial and temporal scales. Now, I thought long and hard about what property should I use, and eventually came up with albedo. Maybe not surprisingly. So what we're going to do is we're going to use albedo as an example to look at the impact of spatial and temporal scales. And we're going to start off by taking this plot that has space on the x-axis, time on the y-axis, and just to start fill it out. For albedo, what part of this do we have to really worry about? And what I'd ask you to do is pay some attention to albedo, but while you're sitting there, think about, how does my favorite parameter go on this plot? How's the process I'm most interested? How would I fill this graph up? In terms of albedo, we can start out, I sure want to know what the albedo is right here today. In fact, I want to know what the albedo in this room is today. And that's what we have here, looking at albedo on a daily time scale from meters to a couple hundred meters. So we certainly want to know that. Now, I talked about the importance of seasons, and particularly the summer melt season. So I really want to know albedo over time, at least for a year. So that fills in a little bit more of this area. And if I have that albedo data for this area over the course of one whole melt season, I want to actually understand what's causing the changes. So that means I'm going to have to take a close look at the ice properties, because basically the albedo is strongly influenced by the physical properties of the ice. And I think most of the sea ice parameters of interest ultimately are connected to physical properties. So I filled in a fair amount of this. But really, is it enough to represent the entire Antarctic or the entire Arctic just by something the size of a couple football fields? Well, no, we want to look at larger scales. We want to look at larger areas. We want to look at regional scales, which means we have to tie things in somehow, either with aircraft imagery, satellite photographs, or large-scale modeling. So now we've filled up a fair amount of this. And then we remember that way back 5 minutes ago, I talked about how important decadal timescales were. So we really need to fill this out on decadal timescales. And so here we are, we filled this whole thing out. And my guess is if you're thinking about your parameter, you'll come up with something similar. Now, realistically, we're not going to go out and drill ice cores across the Arctic and the Antarctic, but there are ways that we can do some experiments, we can do some modeling, so we can just pick off key points on this and extrapolate that. So let's take a look at that, again, in the case of albedo. We can start out by looking at that first block I was interested in. What's the albedo today from here to the next building? And that's what's shown here. These are results of albedo measurements made on cold, dry snow in April, going along a line that was 100 meters long. And we see that's really pretty nice. The albedo is around 0.85, 0.9, and it doesn't vary much spatially. So that's good. It's simplifying, and that it means that we don't, when we have cold snow, we don't necessarily have to measure things in a lot of places. Now we can come back a month later when the snow starts to melt, and we see that there's been a slight decrease, and then also we still have this spatial homogeneity. And we can look at the properties of the snow and say, okay, we see a decrease, we need to be able to explain that. Because if we can explain it, we can extrapolate. And we look at the snow and say, oh, what used to be cold snow with small grains and lots of air-ice interfaces and lots of scattering, now are larger grains with water filling in some of the air voids and less scattering. So it makes perfect sense that the albedo is less. So then we come back another few weeks later, and the snow's all gone. And now what we have is bare ice, a couple of melt ponds just starting, and again, we see another drop in the albedo. We're starting to see some spatial variability due to the fact we're starting to see a couple of melt ponds. And again, we can look at this and explain it. Of course the albedo is going to decrease when we remove the snow, because snow's around the best reflector you can get. And then we come back another month and a half later when the melt season is in full swing, and we see now there's a big difference. There's a decrease across the board in albedo, and there's a big increase in spatial variability. Depending on whether or not you're in a melt pond or you're in bare ice, you can get variations in albedo of up to a factor of 4. And this gets a little bit complicated. Up until this, things were fairly straightforward, but here, once we have the melt ponds, things get complicated, and it's more difficult to make simplifying assumptions. So this is one way to look at things, to just take a few snapshots looking over space. Another way to look at things is to just stay in one place and measure the albedo day after day after day. And that's what's shown here, a time series starting out with snow-covered ice, a large albedo, the snow melts, we have bare ice through the summer, and then we get some more snow in the fall. And this is really interesting because if you look at it, that bare ice albedo spends 2 months in the summer just kind of bouncing around between 0.6 and 0.7. So that's really kind of an interesting thing, and when you're making these measurements, when you see interesting things, you have to really be able to explain them. And so in the case of this, we can look, and sea ice has an amazing surface scattering layer. It really is amazing because if you look at these two images, one from June 17th, another from August 7th, you can see how the melt ponds have really developed, in some cases to the point where they've melted through the ice. But if we look at the bare ice, it looks exactly the same. It looks like it hasn't changed at all. But we know that during that period, we melted 0.5 meter of ice. So what's going on? And what's going on is there's a surface scattering layer. You can go and you can pick it up in your hand, you can shovel it, and it looks like coarse-grained snow. But what it really is deteriorated ice, because ice is translucent, some sunlight penetrates, it causes more melting at the grain boundaries. If that ice is above freeboard, the meltwater drains and the ice just falls apart. And this surface scattering layer is interesting because it's self-renewing. You can go out and shovel it off and come back the next day and you have another surface scattering layer. It can vary in thickness. It's around a few centimeters thick. It gets thicker on sunny days when there's more penetrating shortwave, thinner on cloudy days when there's less. And that explains why we see these oscillations between 0.6 and 0.7. So we have the surface scattering layer, and again, in order to explain the albedo over a large scale in terms of bare ice, we have to look at the small scale of these particles on the surface of the ice. So now we see what the albedo is for bare ice. We've explained what it is. There's one last question we should ask ourselves, and that's, does it matter? When we're exploring this plot of space and time, whenever we find something, we should ask, does this really matter? Is this something I have to consider if I'm going to a different scale? So in the case of the surface scattering layer, we can check that out. What we can say is, does it matter in terms of the solar heat input, whether we have a surface scattering layer or not? And so what we have here is a plot over time from February to October. This is just a typical incident shortwave radiation. And what we have are two possible paths for albedo. One where we form a surface scattering layer and another one where we don't. And in the beginning, they're the same because we have snow on the surface. And if you have an optically thick snow cover, it doesn't matter if you have ice underneath it or if you have a parking lot underneath it, because the albedo is being determined by the snow. And it isn't until that snow melts that we have a difference. The blue curve represents having a surface scattering layer with an albedo of 0.65. The red curve represents if we didn't have a surface scattering layer. And if we didn't, we would get an albedo around 0.4 for the ice. And so we can just then use this, calculate the difference in solar heat input, and see that it's a difference of a few hundred megajoules per meter squared, which translates into potentially melting over a meter of ice. So this makes a huge difference. I think in part the surface scattering layer is why the ice survives the summer. Because if we look at the sea ice that's out there now, it really wouldn't do well if it had another meter of melt. So we looked at this now. We can understand what's going on in snow, surface scattering layer, and that it matters. There's other things that we need to look at when we're comparing these different scales. Again, on a temporal basis, we're interested in decadal changes. And one of the big decadal change that we've noticed is the change in the Arctic ice cover in terms of the age of the ice. So we see here all the colorful things are multi-year ice. The blue is first-year ice. Back in '88, the Arctic basin was pretty much full of multi-year ice. Now it's predominantly first-year ice. And so does that matter from an albedo perspective? Well, we can see looking at it, the evolution of multi-year ice and first-year ice does look a lot different because there's a period when first-year ice is heavily ponded. Tends to be flatter, and so what happens when ponds form, you get thin ponds covering the whole surface. Now, does this matter in terms of albedo? We can see here are two evolutionary tracks based on observations, somewhat idealized. The red is for multi-year ice, the blue is for first-year ice, and again, they're the same as long as the snow's there. But once the snow is gone, then you see a big deviation, that the albedo for first-year ice drops off very quickly because you have this extensive pond coverage. And throughout the entire season, the albedo on first-year ice is less than it is on multi-year ice. So that's good to know, but we always go back to the question, does it matter? Is this something that we have to worry about? Well, we can do a little experiment and just say, okay, here's a region in the Beaufort Sea that back in the day was nice thick multi-year ice and nowadays is first-year ice. So it doesn't matter in terms of the evolution of albedo and in terms of the amount of solar heat we put in. And so what's shown here, this is just some observed incident shortwave radiation in black, the two albedo curves, and we'll just calculate the solar heat input to the ice, which is just the incident sunlight times 1 minus the albedo for these two cases. And now what we see here, again, multi-year is red, first year is blue. The heat input's the same as long as there's snow, but once the snow is gone, there's more heat input for the first year ice, and a lot more in early June when we see this extensive ponding in the first year ice. If we integrate this over time, we see that there's around 25% more solar heat input into the case with first year ice. And that translates to around 90 centimeters of additional melt, which if it's first year ice, that'll be enough to get rid of it. So again, we see that yes, this is something we have to consider, because if we have first year ice, we'll have a lot more melting than we will with multi-year ice. And again, it's largely because of the ponds. Ponds. If there's ever something that complicates Arctic sea ice, it's melt ponds. And that's why I'm really excited about this conference, because there's several melt pond presentations coming up, and I'm really looking forward to that. Ponds are really interesting. They're the key to the albedo evolution. If we look at the albedo evolution, there's a lot of things we can simplify. We can't simplify the ponds. We have to know about the pond, how they form, how they evolve. Their albedo can be anything from 0.15 to 0.4. And it's not just in terms of albedo we have to worry about ponds. If we're looking at freshwater balances, ponds are storage areas. We can think of ponds in a way as being giant brine pockets, so they impact freeze-up. And there are also flaws in the ice that can contribute to the breakup of the ice cover in the summer. Ponds are really interesting. And there's been a fair amount of work done on ponds, looking at where they form, how do they evolve. And these are some results from work Chris Poloshinsky did. And what you see is, what's shown here are aerial photographs over time of melt ponds, a particular area, how they evolve. And these are LiDAR surveys of surface topography. And if you look at this basically, and this isn't really surprising, is the surface topography of the ice has a large impact on where the ponds form. What's a little bit more surprising is the surface topography of the snow on top of the ice also plays a role in this. And so here we can get an idea of where ponds form, and once they form, how they evolve. And we can just take a fairly straightforward look and say, okay, if we have a pond, what's the water balance? We have water coming in from meltwater. We can have water going out either horizontally through these channels that connect the melt ponds and eventually go into leads, or we can have water, percolating down, through the ice. So it's a balance of all those things, and it gets into some of the basic physical properties of the ice. Now, ultimately, when we care about ponds, we're not just interested in how one pond behaves, but how an ensemble of ponds behave. And before you know it, we're trying to take a look at the large-scale ponding of the ice cover. So here are two images, both taken on August 7th, maybe a kilometer apart. And you see the one image is really covered by lots of melt ponds, whereas the other image has large areas that are completely unponded. And so when we first looked at this, the question was, why aren't there any melt ponds there? But then when you stop to think about it, you can turn that question around. Why are there melt ponds at all? And again, meltwater comes in, water can go out either horizontally or percolating through the ice. So why do we have melt ponds? Well, to look at that, we have to go down a couple scales and look at the small scale. And the rule of 5 that Ken gave us, it basically said, once you get 5% brine volume, you can have pretty good communication. You can have pretty good percolation. So if we look at multi-year ice, these are just typical profiles of temperature, salinity, and brine volume. Salinity near the top, it's very fresh. Its temperatures are -1 to -2, and the brine volumes near the surface are all below, 5. And that's only lower in the ice that they go above 5. So it makes perfect sense on multi-year ice that we would have melt ponds forming, because it's hard for the meltwater to percolate through the ice. Now what about first-year ice? Again, this is a typical profile. We see we have salinities for first-year ice of around 5 parts per thousand. We have temperatures, again, around -1.5. And that gives us brine volumes of 15%. So you would think with the brine volume of 15% and the hydrostatic head in the melt pond that water would all just flush out. Well, again, to understand what's going on, you have to go down several scales and look at detail at the ice. And this is some work that Ken and Chris Polashensky did just a couple summers ago, to look at what's going on in the ice in these ponds. And so what happens, it's first-year ice. We do have a large brine volume. We have meltwater. We have meltwater from snow. We have fresh snow meltwater at 0 degrees. It starts going down through the ice that's, say, at -2 degrees. And some of that water is going to freeze. Not much of it, but some of it. And what appears to happen is it freezes just in the right place to seal off some of these brine drainage features and stop the flow of water. And so this is the case where something that's happening on a sub-millimeter scale can have an impact on the albedo on scales of several kilometers. So it's really a good example of different scales. And it also raises an interesting question, is if you didn't have snow, would you still have melt ponds on first-year ice? Do you really need this freshwater input to seal things off so that the water can stay on the surface? Again, ponds are just really fascinating. So those are some looks at impacts of things on different spatial scales. What about temporal scales? Does timing matter? Does it matter when something happens? Does it matter when a lead forms, or when snow falls, or when melt starts, or when ponds form? Do any of these things really matter? Well, let's take look at a couple of cases. One, does it matter when a lead forms? And again, I'm looking at this from the perspective of albedo and solar radiation. If you were looking at this from an ice mechanics perspective, you'd probably get a completely different answer. So if we look at it, does it matter if we have a lead forming in spring, early summer, or late summer? Well, we can figure that out. We can look and say, okay, again, our idealized albedo evolution over the summer is here, and the albedo of a lead is there. Lead albedos are pretty nice. They're basically somewhere between 0.05 and 0.1. So again, that's another way we can simplify the treatment of albedo on a wide range of scales. And so really, does timing matter? It depends in part on what the difference is between having, say, snow-covered ice albedo versus a lead albedo. And we can see at different times that difference varies. But it's more than that, because what we really care about is how much solar heat is going in. And so what we need to do is to combine that difference in albedo with the incident sunlight. So we take this incident sunlight, multiply it by the difference in albedo, and we can see the difference in solar heat input, which is shown here in these red bars. And what you see is that the peak time is here in June. That before that, even though there's a huge difference in albedo, there isn't enough solar radiation to make a big difference. It's in June when the albedo for ice has started to decline, but it's still rather large, and you have a lot of incoming shortwave radiation that really matters. And out here in August and September, it doesn't really matter much, again, from a solar radiation perspective, because the difference in albedo isn't as much. And in September, when you have new snow and the albedo goes up, you just don't have much incident shortwave radiation. So for a lead opening, for a sunlight, it does matter. June has the biggest impact. It doesn't matter if it rains or snows. In particular, it doesn't matter if it rains or snows right when spring goes into summer, because that's really a delicate time of transition, because the ice is right on the edge. The surface energy balance is right around zero, and it doesn't take much to push it into the melt season. So let's take a look at that by considering an example. These are some results from June. And what we see here on June the 4th, the ice is starting to melt. You can look at it, you can see the snow is gone in some places. It looks like it's ready to kick off into the melt season. We'd expect ponds to form within the next couple days. But then it snowed and covered everything up, and that snow stayed for another 10 days. So that snowfall had an impact by just basically delaying the melt season for a couple weeks. Now again, does that matter? What's the impact of that? And we can take a look at that by looking from May through August and looking at the incident shortwave radiation and considering two possible tracks of albedo evolution. One track, we don't have the snowfall, and we just kick into a melt season with lots of ponding. The other one, we do have the snowfall. The dots are observations, and melt is delayed. So we can take that and then compute the daily amount of solar heat input, and more interestingly, calculate the total amount of solar heat input for the red curve, which is what happened, and the blue curve, which we would have gotten if we hadn't had that snowfall. And so if we look at this, there's a difference of around 136 megajoules per meter squared. It's around 45 centimeters of melt. So just by having a day where it snowed instead of rain, we spared the ice 45 centimeters of melt. So these events, if they happen at the right time, can have a big impact. So if we step back and we look at albedo on these different scales, I think the key takeaway is that we can do a lot of simplification. In the case of albedo, you can get a good idea of what the albedo is just with a few questions. Is there snow? Is the snow melting or is it cold? Is there a surface scattering layer? Are there leads? Are there ponds? If you can answer these questions, you can go a long way to getting an idea of what the albedo is. And the key for albedo is it depends very strongly on surface conditions. So that's taking a look at the spatial and temporal scales using albedo as an example, is there a general approach we can make? That are there things that we can learn from this that we can apply to other parameters and other processes? And the question is, can mathematics help us do these different scales? What you see here are a few plots, log scale of probabilities for unnamed features that look a little bit interesting. It looks more interesting when you say what you're looking at. That here we see looking at brine pockets and air bubbles over scales of millimeters. Here we're looking at melt ponds over scales of areas of tens to 100 meters squared. And here we're looking at ice floes over diameters up to 10 kilometers. So here we have some mathematical behavior that looks to be similar for different features on widely different scales. So I think there is some great possibilities to apply mathematics to help our understanding and help us be able to treat sea ice on a range of temporal and spatial scales. So just to summarize a little bit, sea ice certainly spans the scales. We have processes that are impacted at all scales. What's interesting is the macro properties are strongly influenced by the micro properties. Timing is important. When something happens matters. Scaling issues can be difficult, but mathematics can help. And for albedo, the major issues are ponds and first-year ice. We're still trying to figure out how first-year ice behaves. And the question dictates the answer, because you can't be all scales all the time. So what you really have to do is formulate the question, and that'll help guide you as to what scales are the most pertinent. There's a bunch of things I wish I knew that I think have some application to scales. So just to toss those out, how are dynamics and thermodynamics interrelated? What are the connections between those two on a variety of scales? What's the source and fate of heat in the ocean? We put a lot of sunlight absorbed in the ocean. What happens to that? What happens to it on the small scale of an individual flow? What happens to it on the scale of an entire basin? What's the trigger to the ice-albedo feedback? I do a lot of work with the ice-albedo feedback, and it's a very powerful mechanism, but it needs something to start it. And we're seeing evidence of ice-albedo feedbacks in the Arctic, but the question is, what's the trigger that starts it? What are the properties of the snow cover? What's the heterogeneity of the snow cover? What's the impact of first-year ice? And that's a key question because we're really getting a new system that's mainly dominated by first-year ice rather than multi-year ice. Where does all the sunshine go? I talked about albedo. Light transmission is also important. And of course, what about melt ponds? I'm really hoping that by the time I leave at the end of the week, I totally understand melt ponds by listening to the presentations about them. Not wanting to put any pressure on people, but I'm counting on you. And then, are there changes going on with ice dynamics? Has this shift from a multi-year pack to a first-year pack, is that changing dynamics? And how the flows break. I think we're going to hear some stuff about flow size distributions, which is really exciting. But if you have a flow, how do we characterize how it breaks up into pieces? How many pieces, what size distribution of pieces? So these are things I hope to learn this week. And to conclude, just want to leave with the thought that what we're doing with sea ice now, it's always been fascinating, but now it's more than that. It's more than just an intellectual exercise because there are consequences to the ongoing change of the sea ice cover. Consequences that are happening today are impacting people in coastal communities, impacting economic issues such as tourism, resource extracting, impacting geopolitics. Now that the ice is gone, the Arctic is starting to get very interesting to people. And also a major impact to ecosystems in ways that we're just beginning to appreciate what's going on and have a long way to go to understanding what's driving those changes. And then finally, the possibility that changes in the Arctic are impacting weather here at mid-latitudes. So what we're doing, it's very interesting, but it's also important and has a definite societal component. Thank you very much.
Thank you, Don, for a fascinating talk. Good of guessed albedo, eh? So, do we have any questions? Okay. Yes, please, let's see. Yep.
Just about Sweden, because when we see these pictures with different scales on photos, from satellite and from small scale, we should remember that there is ratio of scales. And when we look for big picture, we should remember that ice thickness is 1 meter or 2 meters, much smaller than the size of image. But when we look on small scale with ice cores, so all scales are similar. So then I just think that it is not the same, big scale and small, just because of scale ratio.
Yeah, that's really a good point. That on the large scale, things are big. You know, the aspect ratio is a lot different.
Yes, please, John.
Yeah, you mentioned, you asked about the connection between dynamics and thermodynamics. Which dynamics were you thinking of?
Ice dynamics, floes moving around, breaking up in the winter, crunching together. I mean, there's a question that does winter dynamics precondition ice for summer melt?
Thanks, a great talk as always, Don. I really enjoyed listening to you. But I do one question regarding the melt ponds, because you made it sound as if the main reason for why we have melt ponds on sea ice, and first-year sea ice, is the fact that the ice becomes impermeable underneath these melt ponds. And my understanding has always been that these melt ponds are usually just at sea level.
Yeah.
So the pressure head is basically
Yeah.
out there. And so my understanding was that this cutting off of the melt ponds and the sea ice is the reason for whether the two interact or not. But not whether we have melt ponds at all.
Yeah, thanks for bringing it up. That's an important distinction. That what I showed here is the initial melt ponds in the very beginning, when those ponds are still above freeboard. And so what happens is you get the ponds above freeboard, then things warm up, we get more meltwater, then we do have percolation through the ice. The level of the ponds drop to sea level, but they're already there. So I think it's something that, you're absolutely right that for most of the season, the ponds on first-year ice are at sea level. But at the very beginning, when they get started, they're typically a little bit above sea level.
So going back to your list of things you wish to know, which one you wish to know first?
Oh, why don't you just ask me which of my children I like the best? I kind of go back and forth. Where I am today is the source and fate of heat in the ocean. And I'm not just saying it because you asked. Melt ponds are a close second. And the dynamics, thermodynamics is there. And the reason is that from what we've seen looking at changes in the sea ice mass balance, that we are seeing more surface melting, but we're seeing a much larger increase in bottom melting. And there's some interesting questions, like in the summer we pour all the solar heat into the upper ocean. Okay, some of it goes to melting the ice, but some of it is just in the upper ocean. And how that is extracted in the fall makes a big difference. Because if you want to grow ice, you want to get rid of all that heat and then start growing ice. Because if you start growing the ice, then you'll have that steady ocean heat flux for the whole winter impeding things. So this week, that's my most interesting thing, with melt ponds a close second.
Thank you very much. My name is Alexander Korovkin, one of organizers of this program. In terms of mathematics and your presentation, so it's good to know that there are many suspects and which change everything in terms of ice and its performance and others. But if we make a list of the all effects, even we arrange that list, but it would be too long, it's not very helpful, right? So we cannot start with the analysis. So we're just collecting that information, making database, big database, huge database. So now we are concerned how to deal with that, but we are not approaching in this way to the analysis. So from that point of view, it would be helpful to have a list, say, of the effects which have no importance. Like from your presentation, I understood that the under ice currents has no effect at all. Or what's happening under ice, or the could be internal waves, could be topography, anything else. So it's not, didn't appear. So you showed what's happening on the surface.
Right, and that's really, that's a good point, that's a consequence of me mainly talking about albedo, which is impacted by the surface. And certainly what's going on in the ocean makes a major difference. I think one of the things is that there's been a real effort in the past few years to make a stronger connection between people making observations and people doing modeling, so that the models help inform the observations. And I think there's really, that's what's one of the things to me is very exciting about this workshop. It's a way that we can start to make connections between mathematics and models and observations. So we can do exactly what you said, say, okay, we can't do everything. What are the most critical issues, and what tools can we best apply to address those issues?
Okay, thank you very much. I think it's time for coffee now, but maybe just thank Don one more time.